Want to do anything interesting? Welcome to college. No, you should get out and do interesting things. There's always like fun stuff happening on weekends in Providence. There's like festivals and 5Ks and AS220 and all kinds of good stuff. So yeah, make the most of it. Besides, once winter comes, it's, as we all know, winter is coming, and once it comes, it's over. So make the most of Providence. All right, welcome back. But I'm very glad to hear you spent your weekend with the right priorities. What I want to do today is I'm going to start with a little bit of a programming task for you. You are welcome to use your laptops for the next few minutes, so long as you're focused on actually doing programming. Facebook can wait, or Instagram, or whatever you cool kids these days use. So if you want to use a laptop, you're welcome to. This is also going to be something that will work just as well on paper. Not expecting you to run it. If you want to work on it on paper, that would be my preferred thing to do, but you are welcome to do whatever you want. Okay? So I'll give you a minute to fire up your laptops if you want to use your laptops, but just keep in mind that's not at all necessary for what we're going to do. Okay, so here's the deal. I'm going to give you a programming problem, all right? This is something I think would make more sense to work solo on, so work on your own. I'll give you about 3 or 4 minutes to 2-3 minutes to work on it, and then we'll talk about it, and then solutions to it, why I gave it, etc., etc. It'll be most of the rest of class. All right? Good? Well, good. Everyone ready? Anyone need another second? Raise your hand if you need more time. Okay, good. Here you go. Okay? So the problem is you're given a program that takes a list or array of numbers, right? If you can, I don't even care which language you use. And what you want to do is you produce the average of the non-negative numbers that occur before an optional minus 999. That's the problem statement. Okay? You're given it as an input, so you don't have to do any input-output. If you know what that is from your prior programming, use whatever language you want. Go. I want you to try to actually write code. I mean, it doesn't have to be, you don't have to get your colons and semicolons exactly right, but I want you to have actual code-like things on page, right? So don't just think abstractly, actually try to write code. It says the minus 999 may not be there.
But it says in the way, so the strength is 99. So if it's
There might be the value minus 999 in the list.
in the list, but we have to up to, so we can have negative numbers in the list up to negative 99, but we have to work on. So you have.
It's right there. I believe your question is answered by the problem statement. There's nothing in it that says you won't have negative numbers.
Right, but we have to work on this number.
If you want a little more time, give me a gentle hum. Let's say 2 more minutes. Okay, let's do another quick humming test. How many of you want more time? Okay, that's pretty, okay, I'll give you another like 30 seconds. I promised you a minute anyway, so I'll give you a minute. Start wrapping up. Fifteen seconds. Okay, can you hear me in the room now? Very good. All right, screens down. Let's get back here. 5, 4, 3, 2, 1, and we're back. Good. Okay. This problem is actually a very famous problem in computing education research. It's called the rainfall problem. So the idea is you want to imagine that what you've got is a sensor, and the sensor is reporting the rainfall values, but sometimes the sensor goes a bit wonky, and so it throws out negative numbers because it's just like a weird sensor, and you want to ignore those values. You want to average the remaining values, and the point when somebody flicks the sensor off, it sends a minus 999, and you want to ignore all subsequent values because they're basically noise. Does that make sense? Right? It's a little contrived. If you work with real data sets, you'll find that it's not contrived at all. In fact, it is a gross oversimplification of what working with real world data is like, which you will find out because we're going to do some of that later this semester. Okay? After we've gotten more programming skills down, we're going to actually do that in the last few assignments of at least the last 2 assignments of the semester. Okay? Good. So, this problem is called the rainfall problem. And it's been used as a test in computing education for about 30 years now. And the short summary of what we've learned from this is basically it's a disaster. Okay? So the problem was first invented and put out by a person named Elliot Soloway in 1986, and he gave it to 116 students, and essentially over 75% of the students got it wrong. Now, he wasn't trying, his assumption was this is a simple enough problem that students would have no difficulty solving it. What he was really trying to study is how do students decompose a problem? Okay? If you give them a problem that's just more than trivial, how will they decompose it? What are the different structures by which people might try to solve this problem? Okay? And we're going to see that, I'm going to make that very concrete in about a minute. Okay? That's what he really wanted to study. But he handed this out, and basically nobody could even get it right, so there was nothing to study at that point. Okay? Now, admittedly, he did it at Yale, so, you know. But, you know, that's still a bit of a concern. So people said, oh, come on, this can't be so bad. So a bunch of people have redone this study over the years. So, for example, in 1994, a guy named Abrahami gave it to his students and found that, well, we'd gone from 75% to 70%. Actually, we hadn't really. 71% had 3 or more errors. Now, if you're like me, you're looking at this problem and thinking, how could you have 3 errors? What can you possibly do to create 3 errors in a problem statement that's 1 sentence long? And in fact, the average is about 4 to 6 errors per student. Okay? And so, in fact, this led to a lot of angstful discussion about curriculum design. And as recently as 2013, a person named Simon down in Newcastle in Australia gave this problem out to 150 students. So we're not talking like, oh, 3-student class, right? I mean, you can get anything you want out of a 3-student class. But he gave it to 150 students and found that not only did 36% not have pertinent code, it's pretty obvious from the problem statement that something has to iterate, right? Whether you use recursion or loops or something like that, you got to do something multiple times. And 46% didn't even have that. Okay? So this is like a giant WTF, right? People basically took the position that programming is obviously much harder than we thought, and we have to figure out, like, maybe we're asking for too much in our intro programming classes. So what I'm really, by the way, doing is exposing you a little bit to what the research is in computing education, right? Today is actually a research talk. You don't realize it, even though I made you write code. It's actually a research talk. I'm giving you a little bit of a sense of what computing education researchers might think about. Question, comment.
Were they able to touch their code?
So there's a great question. This is exact. So I'm giving you a sample of 3 out of like dozens of things, okay? And people have tried every possible combination. Some people did it in class. Some people did it as a homework. Obviously, if you do it as a homework, they have the full resources of homeworks and TAs, all sorts of things, right? So I don't remember the details for every one of these papers. Trust me when I say that people have tried every configuration and it's been bad, okay? Yeah. It's so bad, actually, that there's a very well-known researcher named Mark Guzdial who has a very good blog on computing education, and he basically said, look, this should be thought of as a challenge for which we should make measurable progress, right? It's computing education research. We repeatedly conduct studies showing just how little students are learning. Let's show we can do better. Why is it that after 30 years we still haven't beaten the rainfall problem? In fact, what if we designed a course with the goal of beating the rainfall problem? What would that look like, right? That's obviously a little extreme, but it's the case that in 30 years, if you haven't made progress on something, one of 2 things is the case, right? Either we have grossly misunderstood students' cognitive abilities, or something's wrong with the way we're teaching the material. Right? I mean, I suppose you can generate other possibilities, aliens, etc., but those seem to be like the 2 reasonably dominant hypotheses. Okay? And there's actually more on that blog post. It's pretty interesting, but I'm not going to go into that for a moment. But let's first understand, If I asked you to rate this problem on difficulty, now that I've told you this, you might change your rating. But before I told you this, how would you rate this? Like, let's take like a low, medium, high, okay? So don't monitor your neighbors, right? The whole point of the humming is nobody has to raise their hand and feel embarrassed. That's the whole point of the humming. So how many of you rate this as a low difficulty problem? Medium difficulty? High? Okay, all right. So some of you might felt it's okay. Some of you may have felt it's high and were embarrassed to hum. That's okay, right? But it seems to be on the low side, right? So I assume your instinct then is my instinct when I first saw this, asking, how on earth can you make 6 errors in this program? Like 1 error, sure, 2 errors maybe. In fact, I do this problem whenever somebody visits, like I have a research visitor, like Peter Norvig, people like that. I make them do this over lunch. This is like my standard lunchtime parlor trick now. Yeah.
Wait, what's an error? Like how big is
Yeah, that's a question of what counts as an error. Well, in some sense, an error is failure to solve the problem as defined, right? So I will show you how you can actually get this wrong. It turns out this is actually a very cleverly designed problem. Okay, so Solvay knew exactly what he was doing when he constructed this problem because there's actually several subtasks here, right? One of them is you need to truncate at that -999, that sentinel value. Another one is you got to remember to ignore the negative before the sentinel, okay? Another one, obviously you got to sum the data and count the data. Then somehow you had to compute the average. And by the way, nobody actually raised your hands and asked, what should I do in the empty case? So almost certainly most of you had at least one possible error by not thinking about the empty case, right? But, yeah. So let me ask you this. Let's have you throw out some of the examples that you came up with. I want to hear some of your, obviously all of you wrote lots of examples before you wrote your code, right? A little embarrassed laugh goes through the room, right? And if you had, you would have caught some of your problems. So how many of you wrote examples, and what examples did you have? Yell out an example. Go.
First I just a list of 1, 2, and 3.
1, 2, and 3. Fine. Okay. What's the answer? 2. Good. Okay. Next person.
-5 or -3, -2, -1, 0, 1, 2.
Okay. Answer.
2. 1. Sorry, 1. 1.
Okay. Good. Next. Go. Okay.
0, 1, 6, -999, 5, and -4.
Okay. Good. Answer.
7/3.
Okay. Next. Yeah.
1, 3, -2, 4.
1, 3, -2, 4.
-999, and then 5.
Okay. And answer.
8/3.
8/3. 8/3. Okay. Any other answer? Any other good ones? Anyone else? Anyone else? Yeah.
-999.
-999. Here's another one. -1, -2, -999. Okay? That's a weird empty input. Right? Okay, good. So, examples. So, the point is, even ignoring weird cases like this, it is actually possible to make mistakes on this problem, and that's where the mistakes come from, right? Any one of these things is a thing you could potentially get wrong. I'm sure you're all you're not Yale students, you're all wonderful. None of you got any of these wrong, but you can see how it is possible for lesser humans than you to make these kinds of mistakes, okay? All right, questions about this so far? You see the problem? You understand where we're going here? What we're trying to do? Any questions? Yeah?
Yeah, for that last one,
Yeah.
isn't it sort of ambiguous, like what that should be?
Well, it's not even just that one. It's also ambiguous in this case. It's also ambiguous in the empty case. These are just clever ways of writing the empty list, right? Yeah. So you can take the interpretation that, well, what are possible answers? What should we do in the -999 case? Yeah. So, throw some sort of raise an error or something like that, yeah?
Return 0 because if it's actually measuring rainfall, then there was just no rain.
Return 0? So, okay, so we have two possible answers. One is that's an error. The other is the answer is 0, okay? So, do you have a different answer?
I was going to counter that one with the
Hold on, we're going to do a little vote here, okay? How many of you vote for the answer? Never mind the mechanism, okay? The answer is it's an error. Okay? How many of you vote for 0? Oh man, okay, you are going to do so badly this semester. Okay, look, It's an error. The average is not well defined on the empty list. That's it. That's all. You don't have to worry about rainfall and all these other things. The empty list doesn't have an average. Right? It could be 0. It could be infinity. The moment you have multiple possible answers, there's no canonical answer that tells you that it's not a well-defined problem on that input. Right? So don't feel badly if you voted for 0. It's not a bad thing to have voted for. But I do want you to think about this kind of question, because I'm going to guess that if you had computing before, and certainly if you had math before, most of the things you were given had well-defined inputs. They were all very nicely, sweetly defined. In this semester, you're going to start dealing with reality where things are not so well-defined. Okay? Sometimes you will get things that have no answer. And starting with the next homework, you'll deal with things that have multiple answers. And in fact, the whole homework is going to be, oh my God, what do we do when there are multiple answers? Okay? Because in the real world, you will deal with those kinds of things. Question, comment? Somebody had a hand up here.
I
Yeah.
was just wondering, in multiple languages, or in some languages, don't they automatically return a division by 0 error, even if you
Yeah,
don't-
so that's a possibility. Okay, this is a really great point. So the comment was, this is on, right? In some languages, wouldn't you get an error if you divided by 0? Okay? How should we think about that comment? Should we say, yeah, that's it, therefore we're done? Well, I mean, obviously the answer is no if I say therefore we're done. Yeah.
Isn't it like we're sort of allowing the program to do the work for us instead of writing a proper program that has a case?
Let's think about that. Okay, so one possibility is we're letting the language do the work for us instead of actually writing a case over there. Yeah?
I was just going to say that seems like reactive instead of proactive.
Oh, I like that. I like the words. Reactive versus proactive. Okay, so we're reacting to what happened rather than proactively saying. These are two different ways of sort of saying the same answer, right? Yeah?
Yeah, I feel like it should be more purposeful how we choose to do it.
More purposeful. I like that. Mindfulness. Yes? Okay, so we should be more purposeful about saying what should happen. There was a hand up over there.
It would be better to like catch the error or throw an error.
It'd be better to catch or throw the error, okay? Another possible answer. By the way, the way things work in this class is I'm going to withhold judgment. I'm going to take answers, right? I'm going to try to merge answers, but I haven't told you what my answer is, right? So don't assume just because I don't respond that your answer is wrong. Could be right, could be wrong. Back there.
The solution probably shouldn't depend on what language we're writing in.
Okay, so there's our principle here. Now you're stating that maybe we should not be so dependent on the language. We should take some explicit steps, yeah?
It's good that we are proactive about it, but as language designers, we should also consider how to catch it for the user.
Okay, but we're not doing language design here. That's the next hour. So good point, but let's not worry about that for now. Yeah, I would love to talk about that, yeah.
Your error should be more descriptive, so a division by 0 error.
Error, that's another way to think about it. What if the descriptiveness of the error?
So you could-
Similar answer? Okay, last comment, yeah.
Pretty much the same thing, but I think if you define your own kind of error for languages that have that,
Okay.
you can kind of list out.
So, we've got a few different principles, right? Essentially, notice that there's a little bit of a convergence here of ideas. Lots of people are saying in somewhat different ways, we should be thinking about what should have happened, right? Now, the business about depending on the language, I mean, in some sense, you are totally dependent on the language, right? I mean, what are you going to do about that? If you're going to write a program, you are to some extent stuck with whatever language you're being asked to program in, and there are going to be things that you get, and you're not going to turn down all of the gifts of the language, right? But it is still the case that what I would like you to do in a situation like this is I would like you to have written these examples, and I guess there's one more, right? There's the one that says just list, right? You can't see the empty list, but it's that, right? So I would have liked you to have explicitly written these and said what should happen. It's less important to me whether you use the mechanism of the language or do something fancy. This is not really an advanced programming course, so I'm not going to teach you all the weirdness that's in Pirate to do this kind of thing. But I would like you to have explicitly said, this is what I want to have happen. Okay? And by the way, in case you're wondering, just like you can say is, you can also say raises. That's how you write a test case for an error. Okay? You write test cases for an error by saying raises, and I'll let you look it up to figure out how the details work out. Okay? Okay? So instead of saying is, you can say raises. In all of these cases, I would have liked you to set that should raise an error because it's ill-defined on the empty list. Notice that in this particular problem, there's actually many ways of writing the empty list. Okay? Yes?
If you put in, when you're writing the program, you put in one of the cases and you say, in this case, it will have to return a certain error, would you write that error as a string? Because then it's possible the header would...
Yeah, well, raises are not part of the header definition. They sort of, they're beyond the header definition. So even if you say my rainfall program returns a number, raises always take strings. That's just how the language is defined for simplicity, okay? Yeah, okay, good. Okay, so far so good. So we understand the problem. We've even made a decision about what should happen here. And the decision in general that I'm going to want you to indulge in this course is I want you to think explicitly about decisions rather than, oh, the language did something, whatever it does is fine. Okay? Even you can just let the language throw the error, right? This isn't a serious software engineering course. So yeah, in a really well-engineered program, you should raise your own errors rather than letting the language errors seep through. But the critical thing is make sure you've thought about this case in the input. Thought about all these cases. Right? That's what I really want you to get as a discipline. Okay. Now, it turned out in that blog post that I talked about, Mark Guzdial actually asked a question. He said, how is it that the people who do like how to design programs haven't thought about this and tried to work on this problem? So in fact, after that, Professor Kathy Fizzler, whose office is over there, actually did a study. So she worked with 5 courses in 4 different schools and coded a whole bunch of examples. So they were using a combination of Racket, OCaml, Pirate, and so on. But they were all doing basically the stuff that you did this summer. Okay? Imagine that they had access to at least the first 3 placement homeworks from the summer. Right? That was what the students had as a background. And what I'm going to do is I want to first talk about what different solution structures there might be to this problem. Okay, so I'm going to put up 3 different solution structures and we'll see which ones each of you had and then we'll talk about what the consequences of that might be. Okay, so here are 3 different solution structures that she identified. The first is what she calls a single loop solution. So in a single loop solution, you just iterate over the whole list one time. You keep iterating till you find a sentinel. And by the way, most of these programs, in fact, were written in a language like Racket or Pirate. So they're actually written using recursion. And those extra variables were basically additional variables for an accumulator program, right? So I'm just simplifying and getting rid of the syntactic details. So you do a single iteration through the data, right? If the next input is non-negative, then you update the sum and count. Otherwise, you leave the sum and count unchanged. At the end, you compute the average. The clean multiple version is basically you do the same thing, but you do 1 iteration for the counting and 1 iteration for the sums. And then the third solution is what you call the clean first. Basically, what you do is you first go up to the sentinel, right? And you basically take the following perspective. I've been asked to compute, actually let me do this first. Let me first ask let's do a little humming vote here on what people in the class had. How many had a single loop? How many of you had a clean multiple? And how many of you had a clean first? Okay, all right. So you're still in high school, good. Okay. What is the essence behind the clean first solution? Clean first solution is recognizing the following. It's recognizing that at the end of the day, the problem you have been asked to compute is an average. Right? That's the essence of the problem, is compute the average. However, you've been asked to compute the average on, you all know how to compute the average if you're given a list of numbers that just told to average that list of numbers, right? You'd probably compute the sum of it, the length of it, divide one by the other. Okay, but the problem is you've been given noisy data. You have the sensor that's sort of malfunctioning, and so the data set you've been given isn't as clean as you would like it to be. So what should you do? Cleanse it. So first you clean the data set, right? So what does that mean? Take the prefix up to the sentinel, remove the negative numbers, right? And now you have a problem that you already know how to do, right? Any of you who've taken math classes have been told, reduce to solve problems, reduce to known problems. That's the same strategy that clean first is following, right? Reducing to a known solved problem, which is how to compute the average. We just have to shape the data to get it into shape. Make sense? Okay, so here's what's interesting. when Kathy went and looked at previous papers, in as much as we could tell, first of all, most of them didn't have solutions, remember, right? 75% had bugs, et cetera, et cetera. But historically, the data had people who typically had either no clear, coherent plan at all, or they had a single loop solution. Okay? And in some sense, it's unsurprising because some of the older papers were written in languages like Pascal that didn't even have built-in data structures. So you had to read a number from the input, do the computation, and do the loop. So you couldn't store the numbers. And if you can't store the numbers, well, there's really not much of a choice, right? It's the only option you have is you have to have a single loop and process everything because you don't get to see the number again, right? What's interesting is in her study, the distribution was vastly different. And it was actually the first time in all of the history of studying this problem in all of computing education that anyone had, first of all, very few errors and an actual ability to see differences in plans. Right? So somehow something was different about students who were working with these curricula, the kind of curriculum you've seen so far, and their ability to not only solve the problem correctly, but also solve the problem in interestingly different ways. Right? And one of the things she then did was to go and look into what things people had used, what kinds of library and higher order functions students had used in the case where they had correct solutions. And that was 187 out of 218. And essentially looked at this library usage and found, unsurprisingly, that clean first students, like single loop, you're not reusing anything, right? You are rebuilding things that are already in the language. Clean first is, unsurprisingly, the one where you get to do the maximum amount of reuse, right? So if you want to count, well, it's pretty natural to use length. If you want to take out the negative numbers, it's pretty obviously a filter. And if you want to do the sum, it's fairly clearly a fold, right? Now, there's a lot more that I could tell you that I'm not telling you about in today's class because this is not, after all, a research talk. This is meant to be an introductory course. But what we don't know is why students are doing this, right? Are they saying, look, I want to clean the data, and I know filter is a good way to clean it, or are they looking at the problem and saying, well, sounds kind of like a filter-like thing, so let me filter and see what filter would do for me, right? So there's a lot more about cognitive science of programming. We've done some of that research, but I'm not going to present here. Just want to point out there are some interesting open questions here, even when you look at this data. Okay? All right. So, why are we even showing you this problem? Why are we studying this problem? Why would I take time out in the critical part of the semester? You're trying to choose courses, etc. Homeworks are coming fast and furious. Why am I talking about this? Because I don't know, I know some of you have had prior computer science, in fact most of you, not all of you, many of you at least, and there's a perspective here that you may not have been exposed to before, right? A lot of the classic problems, just planning or programming problems, many of the things you saw in high school tend to center around things like keyboard I/O and dealing with like reprompting for invalid data and stuff like that. When you start moving on into computer science, you are going to be working with real data sets. Okay? Question, comment? Oh, sorry, input and output, right? So right now we have not taught you a command in Racket or in Pirate for flashing something on the screen and asking for input, right? All of the inputs go as arguments, like at the, either in the check block or in the interactions window, right, at the triple prompt, or and output is also done the same way, right? The language does the printing for you. We haven't taught you a command to say, here's how you print it, and here's how you print it in red, and here's how you print it with bells attached, and here's how you print it so that it flashes on the screen or scrolls at the bottom. We haven't taught you those things. Those are called input and output commands. Sorry, okay? As you move on, you are going to deal with a ton of what is now called data science, okay? And data science is the act of essentially anybody here who's interested in machine learning of any sort, artificial intelligence of any sort, and whether you're interested or not, you're going to be dealing with it. You are going to deal with real-world data sets. Real-world data sets never, ever come clean. Okay? The kinds of issues that I'm talking about here are minor, trivial issues compared to what you will get. And I've worked, for example, with meteorological data. I've worked with computational biology data. It is a gigantic mess. They were produced, first of all, by devices that are flaky. They're produced by people who didn't know any computer science, right? And they were devised by buggy programs. So that's where the data comes from. And you don't get to go back and say, you know, I'm sorry, Meteorological System of America. I wish you would give me better data than this. I'm refusing to process it. You don't get that choice, right? You just get the data you get. And what you need to do is to deal with it how best you can. So one of the principles I'm trying to teach you here is the principle of cleansing data, okay? So modern systems get noisy and unstructured data. They come from files, they come from sensors, they come from web, they come all over the place. In fact, if you do any web programming and you don't deal with badly structured data, you are almost certainly a security violation waiting to happen, right? It's only a question of whether it takes like 5 minutes or 5 days to find the security flaw, but it's one of the two, right? So that's why you have to get used to this idea of getting messy data and dealing with it, right? I'm a big fan. There's a person named Hadley Wickham who's one of the leaders in the data science programming community. And Hadley's a big fan of the language called R, which is widely used in data science. He's the author of a book called Advanced R. And he talks about a lot of interesting ideas about structuring programs in data science, right? And of course, you know, he's got this this tweet that that got famous for a while. You know, why you should use functional programming instead of for loops. An explanation using cupcakes. Anyone want to watch a video? You want to watch a video? Hum of you want to watch a video. Oh boy. Okay. All right. Okay. Okay. Here we go. Let's see if we can get the volume up on this.
Using for loops. This is absolutely not true. But there are some advantages to kind of taking the next step beyond for loops and learning these techniques of functional programming, which is basically, instead of you writing a for loop every single time, you're going to use a function that does the for loop for you. So in some sense, this is all about being lazy. Instead of you doing the work, rely on the work that someone else has done. And so I'm going to try and illustrate these ideas using some cupcake recipes as motivation. So here is a cupcake recipe. This is a real cupcake recipe from the Hummingbird Bakery cookbook. How many of you know about the Hummingbird Bakery? It's a fairly famous bakery here. How many of you have made a cupcake in your lives? Okay. So if you've ever made a cupcake before and you read this recipe, you'll notice it's quite explicit. Right? Put the flour, sugar, baking powder, salt, and butter in a freestanding electric mixer with a paddle attachment and beat on slow speed until you get a sandy consistency and everything is combined. Right? Or my favorite instruction here is continue mixing for a couple more minutes until the batter is smooth, but do not overmix. Right? Worst advice ever. Don't overmix. You can kind of take it as given. Right? Don't undermix it either. Don't overbake your cookies. So this is great the first time you've made cupcakes. So it's very, very explicit. It spells everything out in detail. But now imagine while you've mastered vanilla cupcakes and you want to go on to make chocolate cupcakes. So what is the difference between a vanilla cupcake and a chocolate cupcake? And if I kind of switch back and forth, you might notice, well, so you put cocoa in a chocolate cupcake. And so you can imagine this is like a 100-page cookbook. It tells you how to make cupcakes, and every page repeats this information and changes a few small things. So this is important because now that you've mastered vanilla cupcakes and chocolate cupcakes, maybe you want to go on to invent your own cupcake recipe. It's really useful to kind of be able to easily see what are the parameters that are the same and what are the parameters that are different, but it's hard to follow because there's so much text. So what I'm going to do is I'm going to refactor this recipe. I'm going to rewrite it as if I was rewriting a function to be easier to understand. So one unfortunate story about this cookbook, my friend in New Zealand recommended it. She said this is a really great cookbook. And then I bought it and made some cupcakes from it, and they turned out terribly. And I complained to her and I said this is a terrible cookbook. But it turns out, unfortunately, I bought the American version, which uses these ridiculous, like a scant 3/4 cup of sugar instead of reasonable weight metric measures. So the first thing I'm going to do with this recipe is I'm going to convert it to reasonable units. The next thing I'm going to do is I'm going to rely on some domain knowledge. So I'm going to assume that you've done some made some cupcakes before, or we've done some baking before, and I can reduce the recipe to this. So mix these things together until sandy, and then beat them in with the wet ingredients. Now this amusing historical anecdote is that when I was a kid growing up, I did quite a lot of baking with my mum. And her recipes always really annoyed me because they were just a list of ingredients, and they would say, bake hot oven 10 minutes. And there were never any instructions. It was just assumed that you would know, based on the ingredients, what to do with it. And so at that time, that really frustrated me. So I rewrote all of these recipes with very explicit instructions about what to do. And now I'm rewriting recipes in the opposite direction. So there's one other thing we can do here that's going to make it easier to generalize. I'm going to kind of use some variables. I'm going to say just beat the dry ingredients together and then mix the wet ingredients. And now that I've done that, I can put multiple recipes on a single page. And this is useful because we can now see precisely what is the difference between a vanilla cupcake and a chocolate cupcake. And it's not that you add cocoa, right? It's that you substitute flour for cocoa. So this is useful because now if you made this cupcake and it wasn't chocolatey enough, it's kind of obvious what to do, right? You put more cocoa in instead of flour. Or if it was too chocolatey, you'd put more flour and less cocoa. And now that we've done that, well, the next kind of step is to start thinking about these recipes as data. So I can now put them in a data frame and I can fit on even more recipes on a page. So I've now added a recipe for lemon cupcakes. So what's the difference between a lemon cupcake and a vanilla cupcake? Well, instead of adding vanilla, you add some lemon zest. Right, so this is important because if you want to go on and generalize to create new types of cupcake recipes, now you can kind of see what's the same, what's normally the same, and what's different. Well, here's another recipe, red velvet cupcakes. You can kind of see immediately that these are a little different, right? They have more flour, they have no baking powder, they have more sugar, and they have more butter. So right away you know this is going to make a bigger mixture, but it's not going to rise as much probably. Now, there's one sort of interesting, there's still a one egg, right? Because eggs come in integer quantities. Although, interestingly, if you really get into baking, the integer number of eggs is not really accurate enough, and it's even better to weigh out like 40 grams of egg, which I assure you is quite frustrating. So, what's this got to do with programming? Well, here are a couple of for loops. And I want you to just look at them for a couple of seconds and see if you can figure out what they do. What's the same between these for loops and what's different? So these for loops, so there's 3 parts to every for loop. Your for loop should always start by allocating space for the output. So here I'm going to make a vector of doubles that's the same as one element of this vector for each column in the empty cars data set. It's the first part. You always want to do this or your for loops are going to be terribly slow if you have to grow the output at every iteration. Then we're going to iterate. We're going to say for 1 over seek along. How many of you have heard of seek along before?
He'll explain what that is in a moment.
To just quickly demonstrate that, say we've got 1, 2, 3. You seek, oops, let's not do that. Let's call it. It just gives me a sequence of vectors. A sequence of integers the same length. So it's basically like this.
Gives you the indices.
So what happens if I just have 2 elements in this vector? I get the numbers 1 to 2. What happens if I have 1 element in this vector? So what should happen if I have a vector with no elements in it? I should get no integers, right? And that's what I get with seek along. I get an integer of length 0, but but if I use 1 to link x, r is going to helpfully count back from 1 to 0.
These are some R details you can.
So normally you don't like deliberately use zero link vectors in your code, but you want to protect against accidentally using it because that's not going to give you an informative error message. You're just going to get this weird error message somewhere later down the line. That's
Sound familiar?
You're going to have no idea what to do. So seek along is just a little protection. Okay, so we've got the output, we've got what we're looping along, and then we've got the operation, extract the ith column of empty cars, compute the mean, and then save it in the ith element of this vector. So what's the difference between this for loop and that for loop? Well, we're just computing the mean in this one and the median in that one. So the problem with for loops is that they kind of tend to emphasize the objects that you're working with. Whereas what's actually important is the action, right? This is the critical difference between these two for loops. But it's hard to see it because it's, it's like 5% of the total characters I typed is what's actually different. So it's hard to see what's different if there's a lot of things that stay the same. And so what I think you should do instead, or what you should learn to do over time, is use a function that wraps up that for loop. So I'm going to show you the functions from the per package. These have many analogs in base R, but the functions in per are kind of more consistent and have a few shortcuts that tend to help you out.
Okay, so I'm going to stop the video there because at this point he goes into details of R. And anyway, he's trying to introduce map and filter and fold and so on to these people who you've already done them. You've done a homework. You passed a homework on it, or else you wouldn't be here. Okay, so I want you to understand that this is a perspective that's not just mine. It's something that is evolving in the broader data science community. This is also happening with things like TensorFlow, which is a name that some of you may never have heard of. Most of you probably haven't, but some of you may have, which is the new framework for doing machine learning that came out of Google, and there's lots of related frameworks. And they're actually moving more and more with things like automated differentiation into thinking in terms of higher order functional programming, right? That's one of the reasons I'm introducing this to you, because as he says, this is how you elevate your discourse as a programmer. This is how you make clearer your intent as a programmer, and that's why I'm teaching this to you, okay? If you weren't shown this in high school, that's fine. That's why you're in college. If you were shown in high school, that's great. You went to an awesome high school. And if you didn't program in high school, that's totally cool. Now you know what to be doing. Okay? Any quick questions about this or anything else for the last 2 minutes of class? Yes?
The difference in efficiency versus, say you used when you were cleaning.
How much you know about what a compiler does? We can't talk about that question till you know what your compiler does. We can't begin to. Okay? So the short version of it is, if you have a reasonable compiler, you will not notice any difference. In fact, what happens is, so a Haskell compiler, for example, actually literally turns, if you use, it does a operation called deforestation, which is generally a bad thing, but really cool if you're in Haskell. And deforestation is an optimization that the compiler does to essentially turn your map filter fold program into a loop, effectively. Okay, so you program in terms of higher order functions and it takes care of compiling it down. But so the thing is, until you know what your compiler is doing, you can't even begin to talk about the performance. But even if you did, you'd have to know whether it's deforesting or not, whether whether it's doing loop fusion. There's a few different things that compilers do when they see higher order functions to get rid of any performance penalty that you might have incurred, which itself is not obvious. Because then you have to talk about what garbage collectors are doing as well to understand where your real performance penalty is, and that's like, now we've talked about a whole course. Okay? Other questions? Yes?
Does this mean we should be using higher order instead of recursion?
Yeah, so in some sense, you should be saying goodbye to recursion, right? So recursion is great when you want to be explicit. If you're not sure, recursion gives you this design recipe, right? This suggestion, here's a template. Think about what the recursive calls can do for you, okay? But at some point, once you internalize these operations, you don't need to be writing them anymore, right? So you don't need to be, like, in some sense, your goal is to get rid of recursion, except where it's useful in helping you understand the structure and construct a solution. I will do some recursive programs on the board, like in about a week and a half, we'll be doing that. But that's because we don't yet have the higher order operations for that data type, okay? You can then think about a lab where you will build those for yourself, right? Yes?
Can we use for loops in our homework?
Yeah, they don't do what you think they do, so knock yourself out. Yeah. Next question. Any other questions? Good. Quick, real quick. Go.
If you have cases, let's say you do a link FR and then imply, can you imply multiple things in one line?
No, you get one expression. Next.
How would you truncate a list with -99
Take while. You want to look up operations and let you take elements. Think about building it for yourself. So the point here is not to teach you the pirate standard library. Okay? Think about building a function that takes a predicate and gives you all the elements of the list until a predicate. That would be called take while. While some condition is true, take elements of the list and then stop taking elements of the list. Build that and then use that for cleansing. Okay? Good. See you next class. Bye.